In this demo, we shall take a look at how we can configure and interact with the table per concrete type strategy. We're now back inside Visual Studio and we're looking at the Carved Rock database context where we are configuring the item entity. Remember that in order to use the table per hierarchy strategy, we didn't need to do anything. If-core would simply default to using it. We did make some changes to how the discriminator worked, but in many cases that would not have been necessary. And using the table per type strategy was as simple as adding a call to the use TPT mapping strategy method on our item entity. Well, switching from table per type to table per concrete type should be as simple as that also, but it is not for us. This is because we already have an existing data model on the database where the items table is created and is set up to have an identity column for its primary key. And that's where the main problem lies. As we may remember from the slides, the table per concrete type strategy requires us to use primary keys that are based on a shared sequence, and it does not allow us to use identity columns. Well, actually the table per concrete type strategy does offer us a loophole that allows us to use identity columns instead of a shared sequence. But as we shall see, using this loophole is not a very elegant solution. If we scroll down a bit and take a look here, we can see that some code has been added here which tells if-core that we want our identity columns to start counting from a specific number for each of our subtypes. We do this by providing a seed number for each of them. So here we set up the canned food items to start at 10,000, dried food items at 20,000, magazine items at 30,000, and clothes items at 40,000. And then up here where we configure the items entity, we tell it to start at 1. This gives us some assurance of uniqueness between the tables, and it will actually work. Based on this, we can now tell if-core to use the table per concrete type strategy. We can do this by adding a call to the use TPC mapping strategy method on our item entity, like we see here. And if we create a migration based on this and apply it to the database, our test code will work just as we expect. But as just mentioned, this is not very elegant, and it doesn't really show how simple it is to use the table per concrete type strategy if we do things from scratch. This is probably also the most realistic scenario. Switching from either table per type or table per hierarchy to table per concrete type will probably not be done very often. And in such a case, an approach using seeded identity columns can be pursued. But instead of doing so, we'll remove the code that creates the seeded identity columns, and instead simply use the use TPC mapping strategy method. But this will require us to start from scratch. So for the rest of this demo, we'll assume that our data model was created with inheritance in mind right from the start, and that the table per concrete type strategy was selected for mapping to the database. To simulate this, we've had to wipe the database and remove all existing migrations, since they were built on the assumption that the items table should use an identity column for its primary key. For those of you coding along with the demos, you can find a specific solution in the assets folder where this scenario is set up. If we now create a migration based on this, we get the migration file that we see here. Because we started from scratch, it of course contains a lot of things that are not relevant to this module, since it contains all the setup of the database. But we will focus here on the things that are relevant to the table per concrete type strategy. Before we start on the file itself, we should notice this warning that we see here. It tells us that the foreign key items ID on the entity type item order targeting item cannot be represented in the database. Item is mapped using the table per concrete type, meaning that the derived entities will not be present in items. If this foreign key on item order will never reference entities derived from item, then the foreign key constraint name can be specified explicitly to force it to be created. We get this warning because we no longer have a single table to have a relationship to, but instead we have several. The reason why we didn't see this warning when we used the table per type strategy is that strategy still utilized the items table as its central table from which all primary keys originated, and thus a relationship could safely be maintained through that table. In practice, however, as already mentioned, this is not a problem as long as our code does not attempt to insert invalid data. If we make sure that all the data is inserted by if-core and that we use navigation properties on our entities to populate the relationships and query them, then if-core will make sure that things work for us by guaranteeing that the foreign key column will always contain valid primary key values. And now let's take a look at the migration file. So the first thing worth noting is this bit of code here where the item sequence is set up. That sequence will be used for all the tables involved in the item type hierarchy to define our unique primary keys. And if we look at this next bit of code here, we can see that the sequence is being used to define the primary key on the canned food items table. The rest of what we see here is just like it would otherwise be, and as we can see here, the primary key constraint is also created in the usual way. And as we can see here, the same goes for the clothes items table. Here we can see that the sequence is once again used to define the primary key. And if we scroll down a bit further, we can see that the same is the case for the items table. And that's all there is to it. The rest of the magic is done by EF Core, just as it was for the other mapping strategies. And now let's apply the migration to the database and head over to the Server Explorer and take a look. As we can see here, we still have specific tables for all entities, but if we expand a few of them, we can also see that the table per concrete type strategy creates a denormalized schema since there's a lot of redundancy in the columns defined for the various tables. We can for example see that the description column is present in all the tables that we just expanded. And if we open the table definition for the items table, we can see that its ID column is set up to use the item sequence, just like we would expect. And if we open for example the definition for the canned food items table, we can see that this table also uses that sequence for its primary keys. And now let's take a look at this in action. Let's head over to the console application and try to interact with this new mapping. Once again, we'll use the code that we also used when we demoed the other strategies. And of course, since we started from scratch, there are no items in the items table. So we'll add them once again using the code that we see here. But since we already know the code, let's run it and see it in action. Like before, we'll just quickly move past the first several lines of code where we add the new entities to the database and clear the change tracker. After having done this, let's head over to the Server Explorer. As we can see here, only one entry has been added to the items table. This is because we wiped the database and therefore we no longer have the two items that were originally added. And also because there's no longer any entries for items of derived types. And as expected, we also see that this table only has columns that pertain to the items entity. And if we now take a look at, for example, the canned food items table, we can see that it contains all the columns that are relevant to this type, including canning material production and expiry dates, and all the columns that we just saw in the items table. And if we now open up the clothes items table, we can see that it contains the fabric column along with the columns from the items table. If we now head back to the console application and move the debugger past this bit of code here, we fetch all the items from the items table. And as we can see here in the watch view, we get 6 items back, which are of the various types in our inheritance hierarchy. And here we can see our canned food items, clothes items, and so on. And if we now take a look here in the output window, we can see that for this strategy, EF Core has executed a query that no longer uses any joins. Instead, it has created queries for all types of items and used the union all command to combine the results. This is much more efficient than the joins that were generated when we used the table per type strategy. But of course it is a little more costly than the query generated by the table per hierarchy strategy, which only had to query a single table to fetch all entity types. If we now move one step further, past this bit of code here, we fetch all magazine items from the items table using the ofType method. And as we can see here in the watch view, we get one magazine item back. And if we expand that item, we can see that it's the Climbers Quarterly magazine. If we once again look in the output window, we can see that EF Core has executed a query that simply fetches directly from the magazine items table. This will perform much better than the join that was required for the table per type strategy, and it is also slightly faster than the corresponding query would have been with the table per hierarchy strategy. This is because it does not need to filter on the item type discriminator. If we now take one more step with the debugger, past this bit of code here where we use the magazine items collection to fetch the magazine items, we can see that we've once again fetched the Climbers Quarterly magazine. And in the same way, if we now proceed with the debugger to fetch the canned food items, we can see that this executes a query that fetches from the canned food items table. And the next bit of code here, which fetches dried food items, generates a query that fetches from the dried food items table. And lastly, of course, when we query for clothes items, it generates a query that fetches from the clothes items table. In the demo that we just saw, we once again mapped our model to the database, this time using the table per concrete type strategy. As we saw, we ended up with a denormalized version of the schema that we had when we used the table per type strategy. And we also saw that denormalizing made all the difference in which queries EF Core generated for us. When we explored these SQL statements, we clearly saw that all the joins were gone, and they were replaced with union all or direct queries on a single table. This gives us a vast improvement in performance compared to table per type, and it gives us a better performance when querying leaf type entities than table per hierarchy. As with most other things, deciding on which strategy to choose depends on your use case, but there are some general properties of each strategy to take into consideration. From a strictly object-oriented point of view, the table per type strategy creates a database schema which looks similar to the .NET type hierarchy of our entities. This is because when we use this strategy, we'll have a separate table for each entity that only contains the columns that are mapped to properties explicitly added to that entity. Each of these tables are then related to the table containing the base entity, which contains the properties it shares with all its derived entities, in much the same way that subclasses and base classes are related in C#. Table per hierarchy, on the other hand, stores everything in a single table with potentially lots of empty columns. This might easily mean that we'll end up with a mapping table that looks rather messy. And table per concrete type creates a denormalized schema which leads to a lot of redundancy between the mapping tables for the derived types. Both denormalization and having tables with columns that are mostly empty are things that are often frowned upon. But the advantages of choosing either table per hierarchy or table per concrete type may easily outweigh any such concerns. But specifically related to table per concrete type, we should note, as we also saw in the demo, that it is most easily implemented when we start from scratch with a database that isn't already filled with data. More often than not, choosing the table per hierarchy strategy will be the best idea. This is true for many reasons, and certainly from a performance standpoint. According to Microsoft's own documentation, table per type performs worse than both table per hierarchy and table per concrete type in almost all cases. This is because, as we already talked about, when we make queries in a table per type setup, EF-Core will be forced to join together one or more tables on the database. The concern most often attributed to table per hierarchy is its liberal use of columns, many of which will be empty in most cases. But the fact is that on most databases, empty columns do not incur a significant performance overhead since they're able to handle these very efficiently. And as we saw during the demos, we can use sparse columns to improve performance even more if our database allows it. If we want to have the cleaner and more object-oriented feel of table per type without all of its performance problems, we may consider using the table per concrete type strategy, especially if we are starting from a clean slate. This strategy has similar performance to a table per hierarchy, even if it is slightly slower in scenarios where we're querying for entities of several types, because doing so involves accessing several tables. But with this strategy, at least we're using union all rather than join. This means that it performs much better than table per type. And as we already discussed, the table per concrete type strategy is especially powerful when we're querying for a specific leaf type entity. Just remember that, as we discussed, the database schema for table per concrete type is denormalized. This is frowned upon by some database administrators, and it might also be undesirable for other reasons. But when it comes to raw read access of a leaf type entity or any other query that reads data from a single table, nothing beats a denormalized schema since it completely does away with the need to join tables. But as we saw during the demos, this strategy comes with a somewhat large caveat. If we have an existing data model where we want to introduce inheritance to a model that has already been mapped to the database, chances are that we'll be dealing with base class entities whose ID is mapped to an identity column. In such a case, we must modify that column to start counting from a given seed, and also set up similar seeds for all its derived types. This runs the risk of having collisions in the future if we're not able to set up wide enough seed margins for our entities, and it also goes against the intention of using a sequence to generate IDs. So the table per concrete type strategy is definitely best when we're building our database mapping from scratch and have already created our inheritance hierarchy and thought about how we want to map it to the database. So to sum this up, table per hierarchy is probably the go-to strategy for most applications. It's versatile, it has good performance characteristics, and it is less complex than, for example, the table per concrete type strategy. And it is definitely the best choice in scenarios where we want to query for entities of different types at the same time, because it does not involve any joining of tables. An example of such a scenario is when we want to run queries that query for the base type of our inheritance hierarchy. As mentioned, the table per concrete type strategy might also be worth considering in certain cases, especially when we're mostly querying for entities of a single leaf type. But choosing table per concrete type over table per hierarchy should not be done blindly, even in cases where it might seem like the best strategy. If we consider other strategies than table per hierarchy, we should always make sure to benchmark thoroughly, since changing strategy later on might not be so easy, and the strategy we choose might have significant performance implications. Needs might change later on, and the querying pattern that we saw when we were creating our data model might not be the predominant one in the future. For example, if we choose table per concrete type, and then we later on start seeing an increase in the need to query across several types of entities. So if in doubt, the best choice for almost all cases will be table per hierarchy. And in general, we should avoid table per type because it has poor performance. This last thing might not always be possible in legacy setups, but it is not recommended to choose table per type when we build from scratch.